Hello and welcome to Math 1040 Lesson 22B. This is a follow-up for Lesson 22. In Lesson 22, we learned about a hypothesis test for comparing two population means. In this lesson, we're going to learn about doing a confidence interval for the difference of two independent means. It's sort of just a different way to compare two population means mu1 and mu2 over here by using the estimates x bar 1 and x bar 2. Instead of doing a hypothesis test, we're going to do a confidence interval for the difference of the means down here. So let's quickly review these symbols. Understanding the symbols is very important to getting this stuff down. So we have x bar 1. X bar is always a sample mean. The 1 is just saying this belongs to one of the groups or one of the samples. So it's the mean value of the variable for one of the samples, and it's an estimate of mu1, which is the mean value of the variable for the entire population that the sample represents. We also have x bar 2 and mu2, which is the sample mean for the same variable for a different sample, which represents the population mean of the variable for the other sample. So we'll have some examples later. But basically, we're trying to use these two things and compare them and say, are these two things different? Is one more than the other or less than the other, or are we not sure? And that's what the confidence interval can do. That's what the hypothesis test did, but we can do it with this confidence interval. The structure of the confidence interval is going to look like this. It's kind of a lot. The calculator is going to do all the math for us here. We're going to get a lower bound, which is the difference x bar minus 1, x bar 2 minus the margin of error, and we're going to get an upper bound, which is the difference x bar 1 minus x bar 2 plus the margin of error, and it gives us a likely range for this actual difference of means. It's a little much to think about. Fortunately, when we get down here, we can simplify the result. But let's not jump down there just yet. There is a formula to calculate the margin of error and do all this manually. It's a lot of work, so we're just going to use the calculator to do the work for us. And if we need the margin of error at the end, there's a way to get it from the results. If you're using this confidence interval reference from the one sample confidence intervals, on page 2 we have two sample confidence intervals, and so this lesson maps to this stuff here. Didn't mean that to look like a cylinder, but this is the lesson for today, this lesson. Let's just go back over to the actual lesson though. To actually do a two sample confidence interval, we need to check to make sure these requirements are met. These are identical to the hypothesis test requirements for two independent sample means. But we need two samples to be independent, which means they're from two different groups. Both of the samples need to be random, and either for each sample, either the sample size is at least 30, or that we know that the data that it's coming from is normally distributed or close to normally distributed. And that's the same for sample 2. We'll run this command stat test to samp tint, and just like our hypothesis test, we'll choose pooled to be no, and it's going to give us two values. It's going to give us basically the lower bound and the upper bound. And then we can interpret that by saying we're X% confident. The difference in population means mu1 minus mu2 is between the lower bound and the upper bound. Of course, X is going to be 95 or 99 or 90, depending on the scenario, something like that. And then finally, and I think this is the most important part, is how we conclude. And the interval, the difference is talking about the first one minus the second one. So if what we're going to do is decide if the entire interval is positive or negative or contains 0. So if it contains, or let's go in order. If it's positive, then this is probably true, or we're at least 95% or whatever confident that that's true. And by simple algebra, we can add mu2 to both sides to get that we can be pretty confident that the population mean for population 1 is greater than the population mean for population 2. That's if the whole thing's positive. So that's what this means here. Positive, greater than 0. If the entire interval is negative, where are we negative, then this difference in population means is probably less than 0. And by algebra, we can conclude, we can add this mu2 over to the other side and conclude that the first mean population mean is probably less than the second one. And then the last case is if the interval contains 0, it's basically inconclusive, just like failing to reject a null hypothesis. We just don't know. We have insufficient evidence that either mean is different from the other. One is greater or less or even different. We don't have any evidence to support that. And then finally, the margin of error, if you need it, is we can just take the upper bound minus the lower bound and divide by 2, because it's 2e's worth to cover the distance from L to U. So that's it for the overview video here. See you in the next one.